Fan designs are easy to take for granted, and their subtle tuning is easy to overlook, but subtle changes make all the difference in performance. In this discussion, we're learning from this guy, and he gets tactical in this educational talk.
Blade angle, it's also sometimes called stagger angle in the literature, is a purely mechanical property. So that's the angle between the plane of rotation and the chord line of the blade. So the chord line is an imaginary line between the leading edge and the trailing edge of the fan blade. So that's the blade angle. Angle of attack is something different. That's the angle between the chord line and the relative flow, or the vectorial flow angle.
This is Jacob from Noctua, the computer fan company famous for its engineering and its colors, and not always in that order. Jacob has lots of ideas for engineering the perfect cooling solution, although some of them are more theoretical than they might be practical.
From a fan perspective, you want to have as few fins as possible. The finless heatsink is what the fan likes best.
So, and next year, Computex 2026, you heard it here first. Noctua is launching the bladeless fan to go on the finless heatsink.
Working hard on it.
Yeah. We've run a whole series of these deep dive topics on coolers, fans, and now thermosiphons coming up, and always learn more about what to look for in cooling design and engineering. This time in our educational series, we're talking about fan blade angle, fan blade count, heatsink design, and at the end, we ask Jacob about what the future holds after Noctua's learnings from its latest G2 fan venture. Let's get into it. Before that, this video is brought to you by the Montech HSO1 and HSO2 cases. The HSO1 and HSO2 cases differ by way of a mesh front or a curved glass front. We previously reviewed these cases in our intensive benchmarking process and found them to be overall high build quality, with thermals comparable between the two designs. The rear chamber of the case uniquely brings the power supply forward and perforates the rear wall of the case, allowing for more air movement internally while providing a different look. The HSO1 and HSO2 also invert with minimal effort, allowing the computer to present to the opposite side without needing to reconfigure the entire build. Learn more at the links in the description below. I'm joined by Jacob Dallinger again from Noctua, and we've done a number of these now where it's technical discussions about things relating to fans and coolers. And I think the origin of this topic was I asked you something about like why does the angle change across the length of the blade?
Yes, exactly. There's actually a pretty relatively simple answer to that. When you look at most modern fans, you will see that the blade angle is steeper near the hub than further out on the blade. We have an example here of our A12X25 120 millimeter fan section views of the blades, and you can see the blade angle is 38 degree near the hub and 33 pretty close to the tip of the blade. It's a bit difficult to figure out where to put that section with a strongly swept blade, because if you're just slightly off in the section angle, you will also skew the blade angle. But we'll bracket that down for simplicity's sake. To explain that, we need to look a little bit at how these different angles are defined. Most people refer to what we call blade angle as angle of attack. In fan engineering technology, that would not be entirely correct, because blade angle, it's also sometimes called stagger angle in the literature, is a purely mechanical property. So that's the angle between the plane of rotation and the chord line of the blade. So the chord line is an imaginary line between the leading edge and the trailing edge of the fan blade. So that's the blade angle. Angle of attack is something different. That's the angle between the chord line and the relative flow, or the vectorial flow angle.
What are you trying to achieve as a fan manufacturer or designer when you're manipulating the blade angle? What's like the big picture?
Yeah, I think we can jump to the next slide a little bit for that. The bigger your blade angle, the more airflow you drive. It's pretty straightforward that if you have a very steep blade angle, it will just drive more flow, right, with one rotation. But the problem with it is that you should not overdo it, because the steeper your blade angle, the higher the risk of stall and flow separation. It's like with an airplane, if you drive the blade angle too much, you will have stall, so flow separating from the rear side of the blade. And flow is a big problem in fans or for fan performance in general. It will cause that stall dip, so-called stall dip on the PQ curve. And in acoustics, the turbulence that stall causes the noise of the fan to go up. So you will need to balance that maximizing of airflow versus risk of stall. And generally, from an overall fan design perspective, if you build a fan like this is our venerable S12A with a very steep blade angle.
This is about a 2013, you said, or something?
Yeah.
Something like that, okay.
Evolution of our very first NFS12 fan from 2005. Then there was a follow-up version, NFS12B, in I think it was 2008. So if you build a fan like this, you will end up with that very steep blade angle. You will end up with a PQ curve that's very flat.
Okay.
You will produce very high amounts of airflow, but relatively little static pressure. So as long as the resistance curve of your application is relatively low, like it would be in case cooling applications, you can achieve superior results with that kind of fan. And if you go for a flatter blade angle, this enables the fan to better push air through resistance. It's again, I think quite intuitive that the flatter the blade is, the easier it is to squeeze air through a densely packed heatsink. So the green line would be a fan with a much flatter blade angle that enables it to drive a lot of air through a steep resistance application resistance curves. So those are the basic considerations for flatter versus steeper blade angles.
Okay, if we pick any point on the blade, I don't know if it makes more sense to talk about it near the hub or near the outer edge, but if you pick any point, you know, how much of an impact does the angle have on the performance characteristics if you're doing like, I mean, is a 1 degree change like a drastic change? You know, give me an appreciation for...
Yes, okay. Yes. 1 degree is definitely something that would cause measurable differences.
Okay.
But usually this is something that would be, when you start a fan design project, that would rarely change in later stages of the development. This is something that's usually locked very early, and then you're playing with more minute details to do the fine tuning. So if you got the blade angle wrong by more than 1 degree in your initial design proposal, then you wasted a lot of time if you have to change.
How do you start to even decide on this stuff? I mean, is it all CFD simulation? Is it just this is such a known science that you kind of know?
Oh, well, there's certain things like blade count, blade surface area. To a certain extent, blade curvature, definitely blade profiles that where very good numerical prediction models exist. That doesn't even need to go in CFD to figure out, okay, what's the number of blades we're going to use, what's the rough blade profile we're going to use. All that can be determined if you know your target application in advance before you even start simulating.
Right.
And then it goes into a simulation stage where you would try to figure out whether your predictions and your initial design draft is workable.
Got it. Okay, so then getting back to your slide deck.
Yes.
How do you want to run through it?
I think I've already mentioned that there's this slight confusion between angle of attack and blade angle. And what we call angle of attack in fan engineering isn't the same as blade angle, because blade angle is a purely mechanical or geometrical property, namely the angle between the plane of rotation of the blade, so basically perpendicular to the fan axis, and the chord line of the blade. Versus angle of attack is defined as the angle between that chord line and the relative flow angle or vectorial flow angle. And this flow angle is defined by two other vectors. The first is the axial flow direction. So you can imagine the fan pushing out air, and we assume for simplicity's sake that this is uniform across the entire diameter of the fan, which is not the case, but it will make things easier to explain if you assume it. So we have air going through like that, and then at the same time we have the fan rotating. So the blade is moving within that plane of rotation. And it's the angle between these two vectors that's the vectorial flow angle. So the faster the air is flowing through the fan, or the more air is flowing through the fan at the same velocity, the bigger that angle will become. Key point to explain why the blade is twisted is that this blade velocity, we're not talking about RPM, we're talking about the actual speed of the parts of the blade moving, is much faster at the outside than on the inside. So if you look at that angle, if this vector here became shorter, whereas the axial flow vector stayed the same, the angle would become bigger. And that's why the blade angle near the hub needs to be bigger than towards the outside. And that change in blade angle is not necessarily a change in angle of attack. You can have additionally a different angle of attack near the hub versus outside, but just the fact that the blade is twisted doesn't mean that the angle of attack changes.
Typically I see 11, 9, or 7 blades.
Yeah, that's very typical choices for our applications, but for example, wind turbines would usually have 3, right?
Okay, yeah, sure, yeah.
It really depends on the application. There is no magic number that works best for all applications.
But going back to what you were saying earlier, I guess there's certain applications where it's just understood that you would probably use a certain choice for that. Like, the only place I've seen 11 is like maybe in the only place I've seen 11 used properly is maybe in like high flow, low resistance or something applications.
Typically, yes. I mean, the problem with 11 blades is that it's it also introduces a lot of mechanical constraints. Like it would have to be very densely spaced, very short blades. Yeah. And there's two reasons that speak against increasing the number of blades, or it's more than that, but I would say three key reasons. So one is blade-to-blade interaction. So if you have blades like very close to each other, you risk the wake flow of one blade still like harming the effectiveness of the follow-up blade. Yeah. And the second two key reasons I would say is blade passing frequency, and the general fact that edges, both the leading edge and the trailing edge significantly contribute to the fan's overall noise emission. So you try to minimize edge length. And if you have more blades, you have more edges.
Right.
Because you will have always that fluid displacement occurring at the leading edge, and the more of that you have, the more noise you will produce. And the blade passing frequency is calculated by taking RPM, multiplying with the number of fan blades, and dividing by 60, because the frequency is in hertz and RPM is in minutes. So, for example, for a 9-blade fan with 2000 RPM, you would end up with a blade passing frequency of 300 hertz. Whereas for a 7-blade fan that runs at the same RPM, you would end up with roughly 233 hertz. The blade passing frequency is the key dominant part of the fan's noise emission. It's not the only thing, but it's I would say, most important part, and you often have other spikes that you see in the frequency spectrum as harmonics of the blade passing frequency, because it is interacting with other noise contributors.
That's what I was just about to ask about. Was not a frequency spectrum plot. What does it look like if you have?
You usually will have that main spike, and you can easily calculate it and double check if that's the blade passing frequency by taking the number of blades and multiplying by RPM. So usually that's the main spike you will see, unless there's some sort of other problem, which could be the case, of course. Right. Generally, humans perceive lower frequencies as less distracting than high frequencies. And that is the main reason why, from a purely acoustic standpoint, you would go for as few blades as possible. The problem with all that is, however, that a fan should not only be quiet, it should also perform. Yeah. And like with so many things in fan design, it's always balancing performance versus acoustics. So clearly, acoustically, less blades would be better. 0 would be the best.
Okay. When are you making that? When are you bringing wouldn't that just I feel like we're getting into Dyson patent territory or something.
Oh yeah,
yeah.
the bladeless Noctua
Yeah.
fan.
When are you gonna just bring me a hub next year? This is the new fan.
Should I?
Yeah, just break all the blades off.
This is something people can try at home if they are interested. We don't even need to produce it. Just
buy
break off all
you
your fan
want.
blades.
Yeah.
Enjoy the quietness, but probably performance might suffer.
Yes.
I think it would be very, very challenging to build a 7-blade fan that performs on the same level as, let's say, the A12 X25 G2 we're introducing at Computech. If you go for the lower blade count, that will probably impose so many design constraints that you will have to end up speeding up that 7-blade fan to a level where the blade passing frequency ends up being the same.
Okay.
So if you had to spin up that 7-blade fan to 2,500 RPM to match the 9-blade 2,000 RPM fan, you would be at roughly the same blade passing frequency.
Potentially exchanging the advantage anyway. Yeah.
So we already talked a little bit about blade angle of attack, and how critical that is to ensuring the performance curve you want. And imagine having 7 blades. You do need a certain amount of blade area to get basic flow and pressure performance. But if you need to squeeze that blade area into 7 blades, you're very automatically forced to make them relatively flat.
Yeah.
Because you cannot go for a steep angle of attack if you want to have that blade surface area in 7 blades.
Right. Yeah.
Those will be the limitations you'll have to deal with when you're locked on 7 blades and still want to achieve high performance. And I would say that it's probably more challenging to work with these constraints than properly optimizing a 9-blade design.
Okay.
So for our space, I would say 120 millimeter fans. We're talking now. I would say 9 blades is the sweet spot.
Okay, cool.
Especially if you want to go for good static pressure performance or good performance against high flow impedance. It
seems like any company, when you've produced something you think this is the peak of what we've done at this point, you're talking about, it seems like 9 blades is the sweet spot. How fixed do you think that science is at this point? I mean, do you think in 10 years, is there a chance that Noctua looks back and is like, you know what?
I shouldn't have said that in the interview with Steve in 2025.
Because now it's going to be,
That's totally possible. I mean, you never know in engineering. I mean, on the other hand, fan development has become very refined for quite some time now. I mean, there's so much groundwork that has been done in the 1960s, 1950s, even 1970s. And a lot of it has become extremely refined within the 80s and 90s. The numerical prediction models are so stable that it's, for me at this stage, hard to imagine that there's going to be that game changer that enables us to build, 13 blade fans that perform way better.
It seems like the most likely thing to change the most drastically. I feel like it would just be continual material advances and change, like chemical compositions and things like this. But
I mean, I would say that we did a major step in this regard by going from PBT or ABS or PA to LCP. That was a major game changer because it enabled us to build tighter tip clearances, blade geometries that would be too prone to blade vibration, blade stretch over the years. The dampening characteristics are so much better, so that was definitely a major step. But I'm not sure if there's in our space where we don't want fans to sound like jet engines, if there's so much benefit going for an even sturdier material.
Right.
There would be options. Like of course, you could build a metal fan.
Yeah.
But why would you want to build a metal fan if you want to let it run at like 20 to 25 dB? You would want to go metal or even harder engineering plastics if you want to go, 6,000 RPM on a 120 millimeter fan, or 10,000 RPM on a 120
finger chopper.
Yes, then it could make sense because then you are dealing with a level of vibrations and blade creep, dragging forces, all that could benefit from stronger materials. But for the market space we are targeting, I'm not really seeing it.
Right.
An exception could be the 7-blade challenge, because we've been talking about performance constraints. If you go for a lower blade count design, that should still perform well. But there's also mechanical constraints. Like the bigger you make the blades, the more rotating mass you have attached to a single point at the hub. So that's where a stronger material has more benefit.
One of the interesting things to me with heatsink specifically is there's a distance between the fins, there's sort of the density, I guess pitch, it seems like, but
fin pitch is what we call it usually.
Right, and then...
or fin space.
Right. What are the different types of fins you might employ on a heatsink? And I'll use that to kind of jump to some of the fan questions. Because we were just talking earlier about how Noctua might use 2 or 3 or something different, types.
Yeah.
What does that really mean? Starting there.
That was mostly related to purely mechanical considerations, I would say. So we were talking about the D15G2 cooler, where you have basically the same set or type of fins on the entire upper fin stack. It's different from stack to stack. I'll come to that in a minute, but the upper part on each stack is consistent. And then in the lower part, we have one cutout for the ram. So that's a different fin size. It's a little bit shorter to make more room for the ram. And then since the heat pipes are converging towards the base once we go further down, we need to have another fin tooling that basically has a wider slot opening for the angled heat pipe to pass through, versus the straight ones can still attach to the fin and be soldered to the fin. And that's the reasons why we have different fin types there. So it's purely mechanical. Right. The only performance related difference in fin type with D15G2 is that the rear fin stack is a little bit thicker than the front one. It's just because of the combined pressure capability of both fans working in tandem that we have on the rear fin stack. So we can have a little bit more or allow for a little bit more flow resistance there.
So then for optimizing for it, I mean, what are the different types of things you look for when you strap a fan to the front of a heatsink? You're going to have resistance from the fins, so you have to push through that. You have to make trade-offs, I'm sure, on we could pack more fins in here and it would be a lot more surface area.
100%, yes.
Right, but then obviously at some point, there's so much resistance, it becomes an issue of can we push through that, and then can we push through it without making it obnoxious from a noise level. So what are the optimizations, big picture stuff that you're doing for fin stacks?
So I would say it's once again balancing and trade-offs. Like from a fan perspective, you want to have as few fins as possible. The finless heatsink is what the fan likes best.
So next year, Computex 2026, you heard it here first. Noctua is launching the bladeless fan to go on the finless heatsink.
Working hard on it.
Yeah.
The heatsink, from a heatsink design perspective, you want to go the other way around.
Yeah.
You want to pack as many fins as possible. You want to maximize fin surface area, but not only that, you also want to maximize fin count. Because especially the leading edges of a heatsink fin is where the heat transfer is the highest. So when you look at the heat transfer rate plotted across a heatsink fin, you will see that it's highest at the leading edge. And then there's a boundary layer built up as flow goes along the fin. And that boundary layer is like aerodynamically insulating the laminar flow. So you will have heat transfer dropping off the longer the fin is. So just making the fin longer and longer and longer, it will help, but it will give you diminishing returns. So ideally you would have extremely tightly packed short fins. But that creates a lot of resistance.
Right.
So the balancing act that we have to achieve is that we end up with a resistance curve of the heatsink that is within the preferred operational range of the fan. So when you look at the PQ curve, you can see that knee kind of section, and that's the stall dip here. And you basically never want to push too close to that dipping region, because as we've discussed before, once the fan stalls, it pushes less air through your application, and flow becomes extremely turbulent. So it will sound not as nice. It will be measurable in SPL, and it will be not as pleasant in tone. So you want to design a fan. It can go both ways, of course. You can either design a fan for your heatsink that works well on your heatsink's resistance curve, or the other way around, right. Or both together. That's basically the textbook explanation. But as usual, the textbook explanation only covers half of the story, because there's so much more to do if you really properly want to optimize fan and heatsink. And a lot of that has to do with the turbulence interactions, near field interactions. So when you look at the PQ curve, you have a PQ machine, you know how it operates. Yeah. You're basically just introducing flow resistance without having any object close to the fan.
You can, with the counterblower. Yeah.
Exactly. So it's not like the fan is blowing against fins. It's just blowing against empty resistance, to put it this way. And that is a different thing than blowing against fins. Because blowing against fins will create turbulence. And the question is, how does that turbulence sound? And how does the turbulent wake flow of the fan interact with the fins? This is extremely important because your fan may, especially from a noise normalization perspective, because your fan may sound great in free flow, but if it has a problem dealing with those turbulences and back pressure, it may sound really bad on a heatsink. And that's where the real fine-tuning begins, that you make sure that that fan and heatsink really match nicely from both performance and acoustic perspective. From an engineering perspective, turbulence is just the physical property that you have to deal with and that you can utilize in certain scenarios. I mean, of course, the turbulence that creates noise when airflow hits a heatsink fin is not a desirable thing. But for example, when you look at our G2 series fans, we have these structures on the hub of the fan that we call centrifugal turbulator. And with these, we utilize the phenomenon that turbulent flow better attaches to surfaces than laminar flow. You have the same phenomenon with a golf ball where the dimples reduce drag because there's a turbulent boundary layer forming across the golf ball. So there are examples where turbulence is beneficial. So in our case, with the G2 fan, we don't have an example here, but you can surely find a B-roll for it. This enables us to have better flow attachment at the hub region, where generally things are very difficult due to the general low speeds of the fan blades.
What do you feel like you've learned from the G2 that it makes sense to kind of explore for the next iteration or product? There's got to be learnings where you guys were like, okay, we can't figure out how to get this into this one. Let's apply it to the next one. And I know you're probably filtering, like, is there anything I can say?
I'm just browsing through the list, trying to figure out what I could possibly say without giving too much away. I would say that there's a lot of negative lessons learned in a good sense. So we went through so many different design approaches that turned out not fruitful. That this gives us a very important clues for future products that this and that is something we don't need to bother trying anymore. So that's very helpful.
Filtering out ideas.
I would also say that probably it needs to be a somewhat different design approach to really get another measurable step up in performance. And we have some ideas for that, but I'm sorry, I cannot tell you because it might take a few more years to finalize. And giving those ideas away would be risky.
No problem. Anything else you want to cover?
I think we've went through a lot of stuff.
We've gone through a lot of stuff. So there's a whole series of these now. It's becoming a thing. We've done at least, it was either 2 or 3 last year, and then plus the stuff at the booth, plus the year before that we had some good ones. So I'll link them all below, probably put them in a playlist or something. If this interests you, you can learn more. And Jacob, thank you.
Thank you for having me.
And we will see you all next time.